page 6. Then I have to reload my YouTube there, so I can follow the uploads. Reload the Danish news. Yes, let's try to continue. Well, this is how they are making the Intel processors, CPUs. They are making in the future, or now they're making by this EUV, extreme ultraviolet lithographic. Yes, let's need a minute to myself ready, but the video can, my computer can crash again in a few minutes. So I should not upload this game video, but I just drive American Truck Simulator a few hours and I like to finish uploads. Yes, I not understand much of this, but I like to read it anyway. Read loud, activate, voice, read to end of documents.
Due to different phase shifts from reflection from the UV mask, different illumination angles result in different shifts. This cannot be avoided with balanced dipole illumination. The multilayer is also responsible for image shifting due to phase shifts from diffracted light within the multilayer itself. 65. This is inevitable due to light passing twice through the mask pattern. 66. The use of reflection causes wafer exposure position to be extremely sensitive to vertical flatness and the reticle clamp. Reticle clamp cleanliness is therefore required to be maintained. Small, rad scale deviations in mask flatness in the local slope coupled with wafer defocus. 67. More significantly, mask defocus has been found to result in large overlay errors. 68, 69, in particular, for a 10 nm node metal one layer, including 48 nm, 64 nm, 70 nm pitches, isolated, and power lines. Few correctable pattern placement error was 1 nm for 40 nm mask Z position shift. 70. This is a global pattern shift of the layer with respect to previously defined layers. However, features at different locations will also shift differently due to different local deviations from mask flatness, for example, from defects buried under the multilayer. It can be estimated that the contribution of mask non-flatness to overlay error is roughly 1/40 times the peak-to-valley thickness variation. 71, with the blank peak-to-valley spec of 50 nm, (1.25 nm image placement error is possible. Blank thickness variations up to 80 nm also contribute, which lead to up to 2 nm image shift. 71. The off-axis illumination of the reticle is also the cause of non-telecentricity in wafer defocus, which consumes most of the 1.4 nm overlay budget of the NXE 3400 EUV scanner. 72, even for design rules as loose as 100 nm pitch. 73. The worst uncorrectable pattern placement error for a 24 nm line was about 1.1 nm, relative to an adjacent 72 nm power line, per 80 nm wafer focus position shift at a single slit position. When a cross-slit performance is included, the worst error is over 1.5 nm in the wafer defocus window. 70. In 2017, an actinic microscope mimicking a 0.33 EUV lithography system with 0.2/0.9 quasar 45 illumination showed that an 80 nm pitch contact array shifted -0.6 to 1.0 nm while a 56 nm pitch contact array shifted -1.7 to 1.0 nm relative to a horizontal reference line, within a and /50 nm defocus window. 74. Wafer defocus also leads to image placement errors due to deviations from local mask flatness. If the local slope is indicated by an angle, the image is projected to be shifted in a 4x projection tool by 8 alpha x. DOF/2 equals 4 alpha DOF, where DOF is the depth of focus. 75. For a depth of focus of 100 nm, a small local deviation from flatness of 2.5 rad, 0.14 degrees, can lead to a pattern shift of 1 nm. Slit position dependence. Illumination rotation across ring field slit. Light reflected from curved optical surfaces will generate arc segments. 76. The illumination angles are rotated azimuthally across the arc-shaped slit, right, due to the reflection of an arc-shaped image from each pupil position as a point source, left. 77, 78. The angle-dependent and wavelength-dependent multilayer reflectance distribution pattern is rotated accordingly. The direction of illumination is also highly dependent on slit position, essentially rotated azimuthally. 79, 80, 33, 81, 82, 83. Nanya Technology and Synopsys found that horizontal versus vertical bias changed across slit with dipole illumination. 84. The rotating plane of incidence, azimuthal range within -25 degrees to 25 degrees, is confirmed in the sharp actinic review microscope at CXRO, which mimics the optics for EUV projection lithography systems. 85. The reason for this is a mirror is used to transform straight rectangular fields into arc-shaped fields. 86, 87. In order to preserve a fixed plane of incidence, the reflection from the previous mirror would be from a different angle with surface for a different slit position. This causes non-uniformity or reflectivity. To preserve uniformity, rotational symmetry with a rotating plane of incidence is used. 88. More generally, so-called ring field systems reduce aberrations by relying on the rotational symmetry of an arc-shaped field derived from an off-axis annulus. 89. This is preferred, as reflective systems must use off-axis paths, which aggravate aberrations. Hence, identical die patterns within different halves of the arc-shaped slit will require different OPC. This renders them uninspectable by die-to-die comparison, as they are no longer truly identical dies. For pitches requiring dipole, quadrupole, or hexapole illumination, the rotation also causes mismatch with the same pattern layout at a different slit position. I.e. edge versus center. Even with annular or circular illumination, the rotational symmetry is destroyed by the angle-dependent multilayer reflectance described above. Although the azimuthal angle range is /20 degree, 90, NXE 3491, field data indicate 18.2 degree, 92, on 0.33 NA scanners, at 7 nm design rules, 36 to 40 nm pitch. The tolerance for illumination can be /15 degree, 93, 94, or even less. 95, 96, 91. Annular illumination non-uniformity and asymmetry also significantly impact the imaging. 97. The larger incident angle for pitch-dependent dipole illumination trend across slit does not affect horizontal line shadowing so much, but vertical line shadowing does increase. Going from center to edge. 98. In addition, high NR systems may offer limited relief from shadowing, as they target tie pitches. 98. The slit position dependence is particularly difficult for the tilted patterns encountered in drum. 82. Besides the more complicated effects due to shadowing and pupil rotation, tilted edges are converted to stair shape, which may be distorted by OPC. In fact, the 32 pitch drum by EUV will lengthen up to at least 9 f2 cell area, where f equals active area half pitch. Traditionally, it had been 6 f2. 84. With a 2D self-aligned double patterning active area cut, the cell area is still lower at 8.9 f2. 99. Horizontal and vertical lines exhibit different shadowing across the slit. Aberrations, originating from deviations of optical surfaces from subatomic and LT 0.1 nm specifications, 100, as well as thermal deformations, 101, 102, and possibly including polarized reflectance effects, 103, are also dependent on slit position, 104, 102, as will be further discussed below, with regard to source mask optimization, SMO. The thermally induced aberrations are expected to exhibit differences among different positions across the slit, corresponding to different field positions, as each position encounters different parts of the deformed mirrors. 105. Ironically, the use of substrate materials with high thermal and mechanical stability make it more difficult to compensate wavefront errors. 106. In combination with the range of wavelengths, the rotated plane of incidence aggravates the already severe stochastic impact on EUV imaging. 107. Wavelength bandwidth, chromatic aberration. Image shift due to defocus depends on wavelength. The angular dependence of multilayer reflectance of the object, mask, is different for different wavelengths, leading to different shifts when defocused. Unlike DUV lithography sources, based on excimer lasers, EUV plasma sources produce light across a broad range of wavelengths. 108. Though the EUV spectrum is not completely monochromatic, nor even as spectrally pure as DUV laser sources, the working wavelength has generally been taken to be 13.5 nm. In actuality, their reflected power is distributed mostly in the 13.3-13.7 nm range. 109. The bandwidth of EUV light reflected by a multilayer mirror used for EUV lithography is over and /2%, and GT 270 pm, winking sad smiley 110. The phase changes due to wavelength changes at a given illumination angle may be calculated. 111. And compared to the aberration budget. 112. Wavelength dependence of reflectance, 111, 109, also affects the podization, or illumination distribution across the pupil, for different angles. Different wavelengths effectively see different illuminations as they are reflected differently by the multilayer of the mask. 113, 109. This effective source illumination tilt can lead to large image shifts due to defocus. 114. Conversely, the peak reflected wavelength varies across the pupil due to different incident angles. 109, 115. This is aggravated when the angles span a wide radius, for example, annular illumination. The peak reflectance wavelength increases for smaller incident angles. 116. Aperiodic multilayers have been proposed to reduce the sensitivity at the cost of lower reflectivity but are too sensitive to random fluctuations of layer thicknesses, such as from thickness control imprecision or interdiffusion. 117. In particular, defocused densalines at pitches up to twice the minimum resolvable pitch suffer wavelength-dependent edge shifts. 118. A narrower bandwidth would increase sensitivity to mask Absorber and buffer thickness on the 1 nm scale. 119, 120, flare. Flare is the presence of background light originating from scattering off of surface features which are not resolved by the light. In EUV systems, this light can be EUV or out-of-band, OB, light that is also produced by the EUV source. The OB light adds the complication of affecting the resist exposure in ways other than accounted for by the EUV exposure. OB light exposure may be alleviated by a layer coated above the resist, as well as black border features on the EUV mask. 121. However, the layer coating inevitably absorbs EUV light, and the black border adds EUV mask processing cost. Line tip effects. A key challenge for EUV is the counterscaling behavior of the line tip to tip, T2T. Distance as half pitch, HP, is scaled down. 95. This is in part due to lower image contrast for the binary masks used in EUV lithography, which is not encountered with the use of phase shift masks in immersion lithography. 122, 123. The rounding of the corners of the line end leads to line end shortening. 124, and this is worse for binary masks. 125. The use of phase shift masks in EUV lithography has been studied, but encounters difficulties from phase control in thin layers. 126, as well as the bandwidth of the EUV light itself. 127. More conventionally, optical proximity correction, OPC, is used to address the corner rounding and line end shortening. In spite of this, it has been shown that the tip-to-tip resolution and the line tip printability are traded off against each other, being effectively CDS of opposite polarity. 128. In unidirectional metal layers, tip-to-tip spacing is one of the more severe issues for single exposure patterning. For the 40 nm pitch vertical lines, an 18 nm nominal tip-to-tip drawn gap resulted in an actual tip-to-tip distance of 29 nm with OPC, optical proximity correction, 95, while for 32 nm pitch horizontal lines, the tip-to-tip distance with a 14 nm nominal gap went to 31 nm with OPC. 129. These actual tip-to-tip distances define a lower limit of the half pitch of the metal running in the direction perpendicular to the tip. In this case, the lower limit is around 30 nm. With further optimization of the illumination, discussed in the section on source mask optimization, the lower limit can be further reduced to around 25 nm. 130. For larger pitches, where conventional illumination can be used, the line tip-to-tip distance is generally larger. For the 24 nm half-pitch lines, with a 20 nm nominally drawn gap, the distance was actually 45 nm, while for 32 nm half-pitch lines, the same nominal gap resulted in a tip-to-tip distance of 34 nm. 129, with OPC. These become 39 nm and 28 nm for 24 nm half-pitch and 32 nm half-pitch respectively. 131. Enhancement opportunities for EUV patterning. Assist features. Assist feature OPC. Assist features help improve image of isolated features, blue, to be more like dense features, gray. However, the more effective they are, the greater the risk that the assist feature will print, orange. Assist features are often used to help balance asymmetry from non-telecentricity at different slit positions, due to different illumination angles, starting at the 7 node, 132, 133, where the pitch is ~41 nm for a wavelength ~13.5 nm and Na equals 0.33, corresponding to K1 0.5. 134. However, the asymmetry is reduced but not eliminated, since the assist features mainly enhance the highest spatial frequencies, whereas intermediate spatial frequencies, which also affect feature focus and position, are not much affected. The coupling between the primary